Hi, and welcome back to the next video in the physics series. Today we're continuing our lesson on waves. We're going to examine some physics problems. I have open in front of you the reference table, and we've been using equations W1 and W2. I just wanted to point something out before we start the problem, that I have these two doodles up top over here. The first doodle is a transverse wave, and it shows the vibration direction is up and down while the wave direction is moving to the right. And of course I have a longitudinal wave below it, and these clusters of lines represent the slinky where it's compressed, and this open space are the rarefactions or the stretches. So you have compression and rarefaction. The vibration direction is in the same direction as the wave propagation. Alright, let's get started on some physics problems. In the last video, we left off with question 5, so we're going to pick up with question 6, which says, a sound wave has a wavelength of 5.5 meters as it travels through air at STP. What is the wavelength of this sound in a medium where its speed is 1324 meters per second? So we note that we're dealing with a sound wave, and I have extracted part of the reference table for you, so you know that a sound wave in STP has a speed of 3.31 10 to the second meters per second. They give you the wavelength, that's here in green, and they want to know what is the wavelength or the new wavelength in another medium where its speed will be 1324 meters per second. Alright, let's take a look at the analysis of this problem. It's important to remember that the frequency of a wave is independent of the medium. When a wave is created, it is created at a certain frequency. When it changes medium, even though the wavelength will change, it'll either grow, stretch, or it will shrink, the frequency of generation of the wave does not change. And since that is a constant for all waves, this is what allows us to analyze this problem keeping that fact in mind. So let's look at this analysis on the right side. The frequency is independent of the medium. If we use the V equals F lambda formula, which is in fact formula W1, then we say that frequency is the speed of sound in air divided by the wavelength in air. So if we know that the speed of sound is 331 meters per second, we divide that by the given wavelength in green, 5.5, we know that this is a 60 hertz wave. That means 60 cycles per second. Now, if we analyze V equals F lambda formula for a different medium, we know that the frequency, F, which is 60, is the same. So it's speed in the new medium divided by the frequency of generation. So the wavelength in the new material is 22 meters. And you could see that there is a relationship. When the wave was 5.5 meters in air and it was traveling at 331 meters per second, this new material allowed the wave to travel at 1324 meters per second. Therefore, its wavelength was significantly longer. Alright? Now there's another way to solve this problem. The speed of sound in air is on the reference table, as you know, and we simply compare the speed in the first material to the speed in the second material as a ratio equated to the wavelength in the first material to the wavelength in the second material. Now this little formula right here is not on the reference table, but it's not too hard to figure out this comparison. What makes this legal is because frequency is independent of the medium, and then they set the ratio here, 331 to 1324, 5.5 to unknown. Solve for the unknown, and you get 22 meters. Alright, that was a pretty challenging problem, but it's good because we covered a lot of concepts. Let's move on to another one. Here in question 7, the diagram below represents a wave. They give you 1, 2, 3 sine waves in a row. I added these blue lines to demarcate the beginning and ends of each wave, and I put in the 1 lambda, and 1 lambda wavelengths, so you can see that all these 3 waves are the same, but you have 3 waves that are fitting into 6 meters. So let's take a look at the wavelength of each wave itself. So if 6 meters holds 3 waves, then it's 2 meters long for each wave. One wavelength is 2 meters. Now they ask you what the speed is if the wave has a frequency of 8 hertz using v equals f lambda. F is this highlighted green 8 hertz, and the 2 meter wavelength, which we calculated above off the diagram, gives you 16 meters per second. It's that simple. Let's move on to another one. Here in question 8, we're going to base our answer to the information provided in this graph. A transverse wave with an amplitude of 0.2 meters and a wavelength of 3 meters travels towards the right in a medium with a speed of 4 meters per second. Alright, there's a lot of information. Let's go over it. In yellow, we have the amplitude. That's 0.2 meters. So that's the height from this baseline all the way up to the crest of 0.2. But it's also from this baseline all the way down to this trough. So I've drawn these red arrows here for you so you could see the amplitudes are 0.2 meters. It says that the wavelength is 3 meters. So the full sine wave goes from 0 to 3 meters. The next full sine wave goes from 3 to 6 meters. And then, of course, we have half of a wave, which is 1.5 meters. So a wavelength is 3 meters. And then they tell you the speed is 4 meters per second. So there's a lot of things they could ask you in this question, but they start with which 2 points are in phase with each other. So we need to look at what does in phase mean. And that means that they have the same displacement and are moving in the same direction. The easy way to remember what in phase is that it's the same point on 2 different waves. So points A and C are the same spot on the different wave. So points A and C are the same points on 2 different waves. And that's how you could tell. Let's take a look at a FET to help us with this. Here I have a FET, which is the one you saw in the last video, and I have a sine wave. So here's a sine wave that's being generated and moving to your right out the window. When we want to know what points are in phase, we ask, where are they on the wave? Well, since this wave is moving, it's a little difficult to see. But if we take a look, we can see that this green dot here, it's really called a node, is on the baseline. So here's a full sine wave, and there is another node on the baseline, and there is another node on the baseline. Well, those are pretty easy to recognize, but what about a different point? Let's pick this one right here. This point on this wave is matched exactly by this point, which is matched exactly by that point. Those points are in phase. And if you did a little math, you'll see that they're 0 or 360 degrees apart. Let me just show you real quick. From the base to the peak is 90 degrees. From the peak down to the base is another 90. Base down to the trough is 90. Trough up to peak is 90. 90 and 90 make 180. Another 90 and 90 make another 180. You have 360 degrees from the beginning of a wave to the end of a wave. And then 360 degrees is 0, and we start again. So if they have the same degree measurement, they are in phase. While we're here, we might as well just point out that the peak and the trough, they are separated by 180 degrees. So peak to base is 90, base to trough is another 90. 90 and 90 make 180. So any point that is 180 degrees away from each other, they are perfectly out of phase. That's going to become very important later on when we talk about standing waves. Okay, let's continue with another problem. Here in question 9, orange light has a frequency of 5 times 10 to the 14 hertz in a vacuum. What is the wavelength of this light? Well, since v equals f lambda and v equals c when it's the speed of light is 3 times 10 to the 8th meters per second, solving for lambda, we get c divided by frequency. 3 times 10 to the 8th divided by 5 10 to the 14th hertz gives you 6 times 10 to negative 7 meters. So the wavelength of this light is 6 times 10 to the negative 7th meters, and in a future problem, we could find where that lies on the electromagnetic spectrum. The electromagnetic spectrum is found on page 2 of the reference tables, and even though you don't need it yet for this chapter and they didn't ask you, you could have gone to this chart with this frequency that they gave you, and you could have found the color of this light. And since they gave you 5 times 10 to the 14 hertz, you would see, here's your 10 to the 14th range, it's visible light, and 5 fits between 5.03 and 5.2, so it's a shade of yellow light. Okay, let's move on to the next problem. Question 10 says that a motor is used to produce 4 waves each second in a string. What's the frequency of the waves? Well, frequency is the number of waves per second. Since you're making 4 waves per second, you have a frequency of 4 waves per second, or 4 inverse seconds, also called 4 hertz. Let's take a look at the next one. In this last question, number 11, light is in a vacuum with a frequency of 5 times 10 to the 14 hertz and has a wavelength of how much? Now, we just found out light has its own chart on the reference table, but even without that chart, you could solve this problem. We know that V equals F lambda, but V is the speed of light, C, which is 3 times 10 to the 8th meters per second, divided by the frequency of 5 10 to the 14 hertz. Don't forget that the value of the speed of light is on the first page of the reference table, given as the letter C, 3 times 10 to the 8 meters per second. Dividing by the given frequency, you get 6 times 10 to the negative 7 meters. This is very similar to the problem we did before. That concludes these selected problems for waves. Thank you for watching, and I'll see you in the next video.